Welcome to the lecture on solving word problems using linear equations, part 2. These lecture notes will focus mainly on percent applications, so word problems that involve percents in them. We're going to start with a very common example that you might use in everyday life. The first example says, Sam made a taxable purchase of $31.95. If the tax rate is 6.5%, what is the final purchase price? So first thing we have to realize is that when you go to the store and you buy an object that has a sticker price of $31.95, you have to add your tax rate onto that before you get your final purchase price. So that's where this formula comes from. Purchase price is the original price plus the tax that you have to pay. Now how do you calculate tax? Well, you take your tax rate and you need to change it to a decimal first. So 6.5%, we need to move that decimal 2 spots to the left. So I'm going to have to put a 0 in there and change it to 0.065. So we're going to take that 6.5%, change it to 0.065, and we're going to multiply that by our original price. And that's going to calculate the exact amount of tax that we owe. So if we do that tax, add that back into the original price, then we'll know the final purchase price that we have to end up paying. So let's go ahead and calculate this. We're going to take 0.065 times 31.95. Hit enter. So that's the tax that we have to end up paying. And what we're going to do next is add into that 2.07675. We're going to add back into that our $31.95. So if I go back to my calculator and just add to that quantity $31.95, then my final purchase price is $34.02675. Now, in the concept of money, this would only make sense if we round off to 2 decimal places. Since the third decimal place is a 6, that means we would probably want to round up. So this is going to be 34.03 or $34.03. So final answer, $34.03. Okay, so purchase price was our original price plus our tax, and to calculate tax, you take your percent times the original price as well. So we're going to generalize that example into a formula which we're going to use for several types of problems. These are called original price problems, and basically in these types of problems you usually are looking for the original price of your object, but you know what the new price happens to be. For example, buying a dress on sale, or getting a salary raise and knowing what the new salary is but not knowing what the old salary was. For both of those applications, we can use this generalization. The new price or salary, depending on what problem it is the old price or salary plus or minus the percent of the old price or salary. Now I use plus or minus here because in some problems you want to add in, like for example adding in tax to raise your price, or sometimes you want to subtract, for example if you're getting a discount so your price goes down. So let's use this formula and an example and you'll see how it works. In the next example we have a dress discounted 20% and the sale price is $68. What was the original price? So if we think about this, our new or sale price is calculated by taking the old price minus our 20% discount, which we calculate by taking 20% of the old price. So here is our generalization in action. We have our new price over here. We start with our old price. We're subtracting our 20% discount. So this quantity right here is the discount. So let's plug in everything that we know. We know the new sale price, that was the $68. What we don't know is the old price or the original price, so that's what I'm going to call my X. So X goes here, and X goes here as well. And that 20%, we're going to subtract off that discount. We need to remember to change 20% to a decimal. So we change that by moving the decimal 2 places to the left. So 20% is the same as 0.2. So our equation that we're trying to solve is $68 is some amount minus 0.2 times that same amount. Okay? Now to solve this, on the right hand side we have two terms with x's in them. So the way you want to think about this is they're like terms. So all we have to do is subtract their coefficients. Now this first x has an implied coefficient of 1. So 1x minus 0.2x is 0.8x. And this should seem like it makes sense, because basically if you think back in terms of percents, this is saying 0.8, which is the same as 80% of what is $68. So if you're getting a dress on sale for 20%, what you end up paying is 80% of the original price. So 80% of what is 68 bucks. That's what we're trying to answer here. So let's solve it. We're going to divide both sides by 0.8. I'm going to need my calculator again. So we want to do 68 divided by 0.8. $85. So X equals 85, and that means the original price of the dress is $85. And that seems realistic. If we're getting it on sale for $68, and the original price should definitely be more than that. So $85 seems realistic. Okay, let's try one more example. A salary problem. Anne received an 8.5% raise. If her new hourly rate is $13.02 per hour, what was her original salary? So whenever you see that word original, that's how you know you're going to be using this generalization, where the new, in this case, salary, equals the old salary plus or minus the percent times the old salary. Now in this problem, do we want plus or do we want minus? Since this is a salary raise, we want plus only, because we're adding to our old salary, our original salary. So whatever her original salary was, we're adding in that 8.5% raise to get her new amount of $13.02. So this is kind of the formula that we're starting off with in words. Now what we want to do is substitute in everything that we know. We know what our new salary is. It's $13.02. We don't know what her old salary is. So that's what I'm going to call X. So that means I'm going to put an X in here, and I'm also going to put an X in here. Remember, we're adding because this is a raise, and her percent is 8.5, which is the same as the decimal 8.5%. We want to change that to a decimal, so I move the decimal 2 spots to the left, so that becomes 0.085. So the equation that we have to solve is 1302 equals X plus 0.085X, her original salary plus 8.5% of her salary. Now again, to solve this, on the right hand side you're always going to have these like terms. I've got an X plus a 0.085X. This is like a 1X, remember? So 1 plus 0.085 is 1.085X. And now to finish solving for X, we're just going to divide by that coefficient, 1.085. And when I punch this into the calculator, we're going to have 13.02 divided by 1.085, and we get 12. Nice even number. So our solution is 12 for X, and that means her original salary was $12 per hour. Remember to put correct units on your solution, and since that 1302 was $13 per hour, then that's the same units we want to use for our solution. $12 per hour. Okay, so anytime you see an original salary problem or an original price problem, you're always going to be using this generalization where new equals the old plus or minus the percent times the old. And you're using the percent as a decimal, moving that decimal spot 2 places to the left. Okay, so that's our first type of problem that we're talking about today. The next major category of problems that we're going to talk about are called mixture problems. Mixture problems are very similar to your basic chemistry class. For example, in this problem we want to take how many liters of a 25% acid solution must be added to 80 liters of 40% acid solution to get a solution that is 30% acid. So imagine you're in chemistry class and you have 3 beakers. The first beaker is our 25% acid solution. Our second beaker is our 40% acid solution. We're adding those 2 together to get a 30% solution. The 40% is a higher concentration and the 25% is a lower concentration. So the lower concentration sort of dilutes the 40%, which is why our final solution over here, 30, is in between the 2. So you want to make sure that the percent you put in this box is always between these 2. Okay? So we have our 3 beakers. We're going to mix these 2 together to get our final solution. What else do we know? Well, we want to know how many liters of the 25% acid solution must be added to 80 liters of the 40% solution. So I know I have 80 liters of this one right here. I don't know how much of the 25% solution I need, so that's going to be my variable x. Now over here, how many liters of my 30% solution am I going to have? Well, remember, if you're in chemistry class and these are beakers, you're going to take all your liquid from this beaker and pour it into the beaker with 80 liters. So how many liters are you going to have together? X plus 80. You're just pouring the 2 solutions together. So however much you have in here plus however much you have in here should always be how much you have in your final solution. So these 2 have to add up to your final answer over here. So we've got our percents in the boxes and our amounts down below. So these are kind of like our rates, and these are our amounts. Now to get our equation, what we're going to do is multiply each rate or concentration times the amount of liquid that we have, and we're going to follow the direction of this equation. So we're going to do rate times amount plus rate times amount equals rate times amount. Alright? Now when we do these rates, we want to use decimals again instead of percents. So I'm going to change this 25%, move the decimal 2 spots to the left, so that becomes a rate of 0.25 times the amount x. So this is rate times amount. Plus, the next rate times amount would be 0.4 times 80 equals the last rate times amount, and the rate in the last box is 30% or 0.3, and the last amount is x plus 80. Now one big mistake that's pretty common here is forgetting parentheses. We want 0.3 times the entire amount x plus 80. So wrap x plus 80 in parentheses. Alright, so here's our equation again. Rate times amount plus rate times amount equals rate times amount. 0.25x plus 0.4 times 80 equals 0.3 times x plus 80. That's the hard part, getting the equation. Now we want to solve it. So let's do a little simplification and distributing. This 0.25x stays put. 0.4 times 80 turns out to be 32. And if I distribute my 0.3 across, I get 0.3 times x plus 0.3 times 80 turns out to be 24. Now we want to get our x's together. So I am going to subtract 0.25x to both sides. That gives me 32 equals 0.05x plus 24. Now I want to get my numbers together, so I'm going to subtract 24 to the left side. 32 minus 24 is 8, so 8 equals 0.05x. And then to finish it off, I'm going to divide by 0.05, and 8 divided by 0.05 is 160. Now we want to write out our final solution. So remember, what we're looking for here was how many liters of our 25% acid solution. So look at your amount under the 25% solution box. That's X. So we're looking for X. X was 160. The units that should go on that are liters, because we want to be consistent with the 80 liters that we had given to us. So our final answer is we need 160 liters of the 25% acid solution. Okay, let's try another one of those. Same kind of problem, but worded a little bit differently. This time we have ink worth $100 per barrel will be mixed with 30 barrels of ink worth $60 per barrel to get a mixture worth $75 per barrel. How many barrels of $100 ink should be used? So we want to set this up just like the other mixture problem. We've got 3 different types of ink involved. We've got our $100 ink per barrel. We've got our $60 ink per barrel. And we're combining those two together to get a new mixture that is $75 per barrel. Okay. Now, those are your rates. Instead of having percents, this time we have dollars per barrel, which is, again, a certain type of rate. Underneath these boxes, we're going to write the amounts that we know we have. We want to know how much or how many barrels of ink with the $100 price tag should be mixed with 30 barrels of ink worth the $60. So we know we have 30 barrels of the $60 ink. We don't know how much of the $100 ink we need to make this mixture, so that's where your X should go. Just like in the last example, the amount that you end up with over here should always be the amount that you start with in the first box added to the amount that you have in your second box, because you're pouring the two quantities together. So X plus 30 needs to be the new amount that I end up with in my $75 per barrel mixture. Okay, so here's my setup. I have $100 per barrel, X barrels, $60 per barrel, 30 barrels of that, $75 per barrel, and X plus 30 barrels of that. So to get my equation, we're going to do rate times amount plus rate times amount equals rate times amount. So the first rate is 100 times the first amount, which is X, plus the second rate is 60 times the second amount, which is 30. The final rate was 75 times the final amount, which was X plus 30, and we want to make sure we wrap that in parentheses so that we do 75 times that entire quantity. So here's my equation. Remember, in this one we had dollars, not percents, so we didn't have to move any decimal places around. So 100x plus 60 times 30 equals 75 parentheses X plus 30. Now we want to solve. So let's simplify. We get 100x. 60 times 30 is 1800. And distributing, we get 75x. And 75 times 30 is 2,250. And you can use your calculator to get that. Now we want to get our x's together. So I'm going to subtract 75x to the left side. 100x minus 75x is 25x. Plus 1800 equals 2250. Let's get our numbers together. So now I'm going to subtract 1800 to the right side. So I have 25x equals 2250 minus 1800 turns out to be 450. Again, use your calculator. And to finish this problem off, we want to get rid of the coefficient in front of x, so divide both sides by 25, and 450 divided by 25 turns out to be 18. Now that's what x is, and x was our amount of the $100 per barrel ink. So this is our amount of barrels that we need to have so that we can get the right concentration. So our final solution is we need 18 barrels of the $100 per barrel ink. Okay? Alright, let's try one more mixture problem. This is kind of like the first one we did. It says how many gallons of 12% indicator solution must be mixed with a 20% indicator solution to get 10 gallons of a 14% solution. So let's set up our 3 boxes again. We're mixing 2 together to get a third. What 2 are we mixing together? We are mixing the 12% solution with the 20% solution to get the 14% solution. Remember, the final solution you end up with should be between the 2 that you start with. Okay? Now this problem is a little bit different than the last 2 that we did. We know these rates, those are the percents, and we're going to change them to decimals. So this is going to turn into a 0.12, a 0.20, and a 0.14. Underneath, we want to write the amounts that we have. And here's where this problem differs from the last 2 that we did. Usually, we know either one or the other of these first 2 amounts. In this problem, we want to get 10 gallons of our 14% solution. So here we kind of know the goal. We want 10 gallons for this last amount. We don't know how much of either of these 2 it's going to take to get to that 10 gallons. So we kind of have 2 unknowns here. Now to make the problem doable so that it's solvable as a linear equation, we want to make sure that we only use one variable. So you want to pick one of these 2 initial amounts to be your x. It doesn't really matter which one. I'm going to let x be the amount of the 12% solution that we need. Now if I know that I have x in this first amount and I want to get to 10, then the amount that needs to be in the second box here has to be 10 minus x. And let's think about why that is. For example, if I know that I have 3 gallons of the 12% solution, then that forces me to need 7 gallons of the 27 or 20% solution so that I end up with 3 plus 7 or 10 total gallons. Or for example, if I had 6 gallons of the 12% solution, I would need 10 minus that, or 4, so that I add up to 10 in my total quantity. So if I let x be the first amount, the second amount has to be 10 minus that so that I don't exceed my 10-gallon limit that I'm trying to attain. Okay? So that's a little bit tricky. What we're going to do next, once we've assigned those variables and those amounts, we're now ready to set up our equation, and that's going to be the same that we've always done. Rate times amount plus rate times amount equals rate times amount. So let's write out what that would be. The first rate is 12%, or 0.12. The first amount was x, so rate times amount, plus the second rate is 0.2, and the second amount is 10 minus x. You want to wrap that in parentheses, so you do the entire rate times the entire amount. And that needs to equal our last rate, 0.14, times our last amount, which was that 10 gallons. So we have rate times amount plus rate times amount equals rate times amount. There's our equation. Now to solve it, let's go ahead and multiply and distribute. So I get 0.12x plus 0.2 times 10 is 2. 0.2 times minus x is minus 0.2x. And 0.14 times 10 is 1.4. We have a couple like terms on the left side. 0.12x minus 0.2x turns out to be negative 0.08x. The plus 2 is still there, and this is still equal to 1.4. Now we're going to get our numbers together, so let's subtract 2. So negative 0.08x equals 1.4 minus 2 is negative 0.6. And to finish solving, we're going to divide both sides by negative 0.08. Lucky for us, the two negatives cancel out because we want to end up with a positive answer here. And negative 0.6 divided by negative 0.08 is 7.5. So final solution here. What are we trying to get? Remember, the amount of gallons of 12% solution. That's what they were looking for. So we need 7.5 gallons of 12% solution. And I know it's the 7.5 because that's what my x was. X was that amount, and that's what we solved for. So our solution, 7.5 gallons of 12% solution. Alright, so we've done original salary problems, we've done mixture problems. The next kind of problem that we're going to look at is called interest rate problems. These are pretty similar to the mixture problems with one little difference. So let's read an example first. We have Susie Williams, who inherited some money from her uncle. She deposited part of the money in a savings account paying 2% and $3,000 more than that amount in a different account paying 3%. Her annual interest income was $690. How much did she deposit at each rate? So I'm going to set this up very similar to the mixture problem, but in this case, instead of having 3 boxes, we only have 2 boxes. We have 2 separate accounts going on. We have the 2% interest rate account, and in this case, the 3% interest rate account. The 2 accounts together add up to give us our total interest. So we're going to want to add up the interest we earn from the first account plus the interest we earn from the second account, and that is what this $690 totals to. Okay, so we have our rates, just like in the mixture problems. We're going to be changing these to decimals, so 2% turns into 0.02 and 3% turns into 0.03. Underneath our boxes, we're going to write down the amount of money invested. Now, we don't know exactly how much we're investing. We want to know how much she's putting into each account. So we don't know anything about how much she's putting into the 2% account, but we know that we're putting $3,000 more than that in the 3% account. So which one of these accounts should be our variable? Since we know nothing about the 2%, let's call that one X. For the 3% account, we're putting in $3,000 more dollars than what we put in the 2%. So 3,000 more than X would be 3,000 plus X. You could also have it in the other order, X plus 3,000. Order doesn't matter when you add. So we have our rates, we have our amounts. Now to calculate interest, interest is actually calculated by taking the initial principal, which is the amount of money that you invest, times your interest rate, times time. So in this problem, our principal is our amount invested. Our rate are these rates, 2% and 3%. And in this case, our time is always going to be 1 year because we're asking for the annual interest rate, and annual means 1 year later. So to calculate our interest, we just need an amount times a rate, or a rate times an amount, just like in the mixture problems. So that's why the two problems are very similar. To set up our equation, we're going to do all these rates times the amounts. So our first rate is 0.02. Our amount for that interest rate account was X dollars. For the second account, we had a rate of 0.03, and our amount invested was 3,000 plus X. So I'm going to multiply that rate times that amount. So I have rate times amount plus rate times amount equals How much interest did we earn? $690. Okay, so it's very similar to the mixture problems, and that we're still doing a rate times an amount plus a rate times an amount. The only difference is on the right-hand side. Instead of having a third rate times amount, this time we actually know what that total turns out to be. So we're going to put our interest earned on the right-hand side every time. Okay? So here's our equation. Now to solve it, we want to distribute across our parentheses. So we have 0.02x plus 0.03 times 3,000 is 90, and 0.03 times x is 0.03x. We have a couple like terms on the left side. 0.02x plus 0.03x is 0.05x plus 90 equals 690. I'm going to subtract 90 to the right side to get our numbers together. So we have 0.05x equals 600. And to finish solving, we're going to divide by 0.05. And we get x equals 600 divided by 0.05 is 12,000. Now what did this 12,000 represent? 12,000 was x. And x is our amount invested at 2%. So this is dollars right here. So we invested $12,000 at 2%. How much did we invest at 3%? Well, the amount invested at 3% was 3,000 more than x. So 3,000 more than 12,000 makes this 15,000. So our solution then for how much did she deposit at each rate is she deposited $12,000 at 2% and $15,000 at 3%. Okay? Let's try another example using interest rates. So on this example, we have two investments again that produce an annual interest income of $114. Right away, that's the number that's going to go on the right side of the equation. That's your interest earned. On the other side of the equation, we have the total amount of money invested is $4,000, and the two interest rates paid are 2.5% and 3.5%. So again, we have two boxes. One of them is our 2.5% rate, and the other one is 3.5%. As decimals, moving the decimal 2 spots to the left, this would be 0.025, and this one would be 0.035. Now underneath these, let's write the amount invested. On this example, what do we know about how much is invested? We're told that the total amount of money invested is $4,000. So we don't really know how much we're putting at 2.5% and how much we're putting at 3.5%. But we only want to use one variable. So let's say that we put X dollars in the 2.5% account. How much would we have to put in the 3.5% account to make sure that we're investing no more than $4,000? Well, for example, let's say that I put $1,000 into the first account. That would mean I would need $3,000 in the second account, so it adds up to $4,000. Okay, what if I put $2,000 in the first account? Then I would need $2,000 in the second account, so that it adds up to $4,000. So let's generalize. If I put X amount here, and I want it to add up to 4,000, then I would have to have in the second box 4,000 minus X, so that I get 4,000 on each side. So this amount invested is 4,000 minus whatever you put in the 2.5% interest rate account. That forces the total to be $4,000 invested. Okay, that's a tricky concept right there. So whatever you put in the first box, you need 4,000 minus that in the second box. Alright, we have our setup. Let me clear some space here. And now what we're going to do is set up our equation, and we are going to do it again using rate times amount plus rate times amount. So we have 0.025 times x, this rate times this amount, plus 0.035 times this amount, 4,000 minus x, equals the total interest earned, which was that $114. So here's our initial equation. That's the hard part, setting that up. Now to solve, we're going to distribute. Use your calculator here if you need to. 0.035 times 4,000 is 140. 0.035 times negative x is negative 0.035x. Now we have a couple like terms on the left side. 0.025 minus 0.035 is negative 0.01x. We still have that 140 on the left and the 114 on the right. Now let's get our numbers together. So I'm going to subtract 140 to the right side. So negative 0.01x equals 114 minus 140 is negative 26. To finish solving, I'm going to divide both sides by negative 0.01. So negative 26 divided by negative 0.01 turns out to be 2600. Now what did we just solve for? We found x. What did x represent? X was the amount invested at 2.5%. So this would be $2,600. How much is invested in the other account? Well, remember that was 4,000 minus whatever we put in the first one. So 4,000 minus 2,600 means I had $1,400 left over to invest at 3.5%. So let's write out our final solution. $2,600 is invested at 2.5%, and $1,400 is invested at 3.5%. And there's our solution. Okay, so we've got original salary problems, we've got mixture problems, we've got interest rate problems. The next type of problem we're going to talk about are coin problems. These are pretty famous. You see these quite often in all math textbooks. So let's try one out. What we have here is a coin collector who has $1.70 in dimes and nickels. She has 2 more dimes than nickels. How many nickels does she have? So to be consistent with the other problems that we've worked on so far, I'm going to create some boxes again. The first box is going to be for my dimes. The second box is going to be for my nickels. Now usually in these boxes we write down our rates. And in this case, the rates that we're talking about here are actually like values. The value of our dimes and the value of our nickels. So how much is a dime worth? It's worth 10 cents. Now should I put 10 here or should I put 0.10? I'm going to use 0.10 because in the original problem I'm talking about $1.70. So a dime in dollars is $0.10. So make sure your units are consistent. Nickels, well, nickels are worth 5 cents or $0.05. So I'm going to use 0.05 for my rate. So now we have our rates. Underneath, let's write our amounts. How many of each type of coin do we have? That's what we're trying to figure out. The only thing we know is that she has 2 more dimes than nickels. So if we know that we have 2 more dimes than nickels, which one of these amounts should I start with? Which one should be x? If I let x be nickels, then I need 2 more than that to get my dimes. So the dimes are going to be 2 plus x or x plus 2. That way I've got more dimes than I have nickels, and that's exactly what the problem's telling us to do. Okay, so we have our rates, we have our amounts. What do we want these to add up to? Well, in this problem, we want them to add up to that $1.70. That's the total value. of all of our coins. So we're going to get our equation by doing rate times amount plus rate times amount equals our total value. So 0.10 or 0.1 parentheses x plus 2 plus 0.05 times x equals $1.70. So there's our initial equation. Now to solve, distribute your 0.10x, so we get 0.10x plus 0.2. 0.1 times 2 is 0.2. Bring down our other terms. We have a couple like terms on the left side. 0.10x plus 0.05x is 0.15x. Carry down the 0.2 and the 1.70. Subtract 0.2 from both sides. So 0.15x equals 1.5. And to finish solving, I'm going to divide by 0.15 that coefficient of x. And we get x equals 1.5 divided by 0.15 is 10. Okay? You want to end up with a nice whole number here because we're talking about how many coins we have. So it wouldn't make sense to have a fractional amount of coins. So what did we just find? Remember that x in this problem was the number of nickels. So here that means we have 10 nickels. So how many dimes do we have? Remember the dimes was x plus 2. So 10 plus 2 means we have 12 dimes. So final solution, remember what they're looking for. How many nickels does she have? She has 10 nickels. So even though we found out how many dimes she had too, the question isn't actually asking for that. So you only need to tell 10 nickels for your answer. Okay. We're coming up to our last type of word problem that you need to know how to solve, and these are distance, rate, time problems. There's a formula that you have probably heard of before. It describes the relationship between distance, rate, and time, and that is the fact that distance, d, equals the rate times the time. So for example, if you are driving 60 miles per hour, that would be your rate. For 2 hours, that would be your time. Then 60 times 2 means we've gone 120 miles. Okay, so it's a very common formula that you use, and we're going to use it to help us solve our problems. So in this first example, we have Anne, who gets to school in 15 minutes if she rides her bike, and in 45 minutes if she walks. She walks 10 miles per hour slower than she rides. What is her speed riding her bike? So there's a lot of information in this problem, but what you want to identify is that we're talking about some times, we're talking about some rates, because 10 miles per hour is a speed or a rate, and we have some distance that we're covering, walking from school or biking to school. So that's how I know to use this distance equals rate times time formula. Now to help organize our information, we're going to set up a chart. I like to put the rate first times the time equals to the distance. And I'm going to make 2 rows and 3 columns. The first row is going to be how Anne gets to school when she rides her bike. And the second row is going to be the information for how Anne gets to school when she walks. Okay? So what do we know? Well, we're told initially that it takes Anne 15 minutes to get to school if she rides her bike. That's a time. So I'm going to put 15 minutes in the time column under the bike row. It takes 45 minutes if she walks. So I'm going to put 45 minutes in the time column for walking. She walks 10 miles per hour slower than she rides. Now miles per hour is a rate. It's a unit of rate or speed. So that's information that's going to go in our rate column. If she walks 10 miles per hour slower than she rides, we can assign variables a couple different ways here. Pick one of these to be your x. It really doesn't matter which way you do it, you just want to be consistent. So let's say that I let x be her biking speed. then we know that she's supposed to walk 10 miles per hour slower than she bikes. So if she's biking X miles per hour, then 10 miles per hour slower than that would be X minus 10. And it has to be the X first and the 10 being subtracted from that. Otherwise, you might end up with negatives. Okay, so in these distance rate time problems, what you're typically filling out first are the two rates and the two times that you know. Okay, one of these may be variables, one of them you'll know. So you're filling out these first four boxes. To get the distance column over here, we're going to use our formula. We're going to take the rate that we are given times the corresponding time, and we're going to multiply those together. So the rate for biking times the time for biking would be 15 times x. I'm putting the 15 in front just to make it look a little bit cleaner. For walking, my rate was x minus 10, and my time was 45 minutes. So I'm going to do my rate times my time. I'm going to put the 45 in front, and I want to make sure that I wrap x minus 10 in parentheses so that I do 45 times that entire rate. So remember, when you're getting the distance column, you're getting these numbers by multiplying across your rows. Okay, now how do you get your actual equation? Well, your equation is going to come from this distance column. In some problems, the two distances will be equal. In some problems, the two distances might add up to some known amount. In this problem, which case is it? Well, they have to be equal distances because in both cases Anne is going from home to school. So the distance that she's traveling is the same whether she bikes or whether she walks. So if she bikes a distance of 15x and she walks a distance of 45 times x minus 10, those two distances have to be equal. So our equation is her biking distance equals her walking distance. Now to solve this, we're just going to distribute our 45. 45 times x is 45x. 45 times 10 is 450. I'm going to get my x's together by subtracting 45x. 15 minus 45 is negative 30x. On the right side, remember there's a negative in front of that 450. So when I divide both sides by negative 30, we get x equals 15. Now what did we just find? Remember that x represented the biking rate. So she bikes at 15, and what units would apply here? Miles per hour. Okay, so Anne bikes 15 miles per hour. All right, and that's exactly what they wanted to know. They wanted to know her speed riding her bike, so here is our solution. You could also calculate how fast she walks. That would be 15, that same x value, minus 10, so she walks 5 miles per hour. The question doesn't ask for that, but you could still calculate it. All right, that's our first example of distance rate time problems. Let's try two more. Okay, these are tough. In this next example, we have from a point on a straight road, Lupe and Maria ride bicycles in opposite directions. Lupe rides 10 miles per hour and Maria rides 12 miles per hour. In how many hours will they be 55 miles apart? So I'm going to actually draw a little diagram here so you can visualize what's going on. From the same point on a road, Lupe goes one way and Maria goes another way. We're told that Lupe rides 10 miles per hour, that's a rate, and Maria goes 12 miles per hour. I wrote her arrow a little bit longer because she's going a little faster, so she's going to be traveling farther than Lupe will be. And the question is, in how many hours will they be 55 miles apart? So we want this total distance to be 55 miles. Okay? Now to actually get an equation that you can solve here, you still want to use a chart like we did in the last problem. So I'm going to have a rate column, times a time column equals a distance column. I'm going to have 2 rows and 3 columns. The first row will be Lupe's information, and the second row will be Maria. Now, what are we told in this problem? We're told that Lupe goes 10 miles per hour. That's her rate. So I'm going to put 10 in her rate column. Maria goes 12 miles per hour. We don't know any times at all here. So let's let Lupe's time be x. What would Maria's time have to be? Well, think about the problem again from our diagram. Both girls, Lupe and Maria, start at the same point, and then they bike along for the same amount of time until they get 55 miles apart. So they're actually biking the same amount of time. So if Lupe is biking for x minutes or x hours, then so will Maria. So in this particular problem, their times are equal. Okay? So we've filled out these first 4 boxes. That's what you want to do first. Then to get the distance column over here, remember we're going to take rates times times. So we're going to do Lupe's rate times her time. 10 times x is 10x. And then we're going to multiply Maria's rate times her time. 12 times x is 12x. Now in the last problem, once we found these 2 distances, we set them equal to each other. That's not the case in this problem, because if you look at our diagram again, Lupe isn't biking the same distance that Maria is, because Maria was going faster. But what we do know is that the 2 girls, however far they bike, their 2 distances have to add up to 55 miles total. So if Lupe goes a distance of 10x, because that was her distance in the distance column, and Maria travels a distance of 12x, because that was her distance in the distance column, then the 2 distances together have to add up to 55 miles total. So that's how we get our equation. Instead of setting the 2 distances equal, we're adding them up to that third number, that 55. So look at this equation. It's actually a pretty simple equation to solve. 10x plus 12x is 22x equals 55. Divide both sides by 22, and 55 divided by 22 is 2.5. Now what did we just find? X here was in the time column, so these were times. So this is 2.5 and 2.5. What would be correct units here? Well, since Lupe's and Maria's rates were miles per hour, we want to keep consistent units there, so this is going to be 2.5 hours. So in 2.5 hours, the girls will be 55 miles apart. So to summarize here, we're making a rate time distance chart. We're filling out the 2 rates and the 2 times. Then we multiply across the rows rate times time to get distance, rate times time to get distance. And in this problem, we added the 2 distances together to get a third number. In some problems, like the last one, you might need to set these 2 distances equal to each other. So it depends on the problem what you do with these 2 final values over here. Alright, we're going to try one more distance rate time problem. Okay, Jeff leaves his house on his bike at 8:30, averaging 5 miles per hour. Joan leaves the same house at 9 o'clock and averages 8 miles per hour on the same path. At what time will Joan catch Jeff? So let's understand what's going on. Jeff leaves at 8:30, going 5 miles per hour. Joan leaves at 9, so she's leaving a little bit later, but she's averaging 8 miles per hour, so she's actually going a little bit faster than Jeff is. So eventually she's going to catch up to him, and we want to know at what time does Joan catch up to Jeff. So let's visualize this again. Here's Jeff. He leaves at 8:30, and he goes for a while at 5 miles per hour. Joan leaves at 9, and she's going a little bit faster, 8 miles per hour. And we want to know when are they going to be at the same place at the same time. So when is Joan going to catch Jeff? Alright, so there's distances involved, there's rates, and there's times. So let's use our chart. So I'm going to have rate times time equals distance. 2 rows, 3 columns. 1 row is for Jeff, 1 row is for Joan. Do we know Jeff's rate? Yes, that's the 5 miles per hour. Do we know Joan's rate? Yes, that's 8 miles per hour. Do we know Jeff's time? Here a common mistake is for students to put 8:30 in. Now 8:30 is the time he leaves, but what we want in our time column here is the time that he spent biking, the time he spent traveling. So he hasn't been traveling for 8 hours and 30 minutes. 8:30 is a clock time. Do we know how long he was biking for? No. So I'm going to call that time X. Okay? Now Joan, she left a half hour later. So if Jeff has been biking for X hours, how many hours has Joan been biking if she left a half hour later? Well, she's going to be biking for the same amount of time as Jeff, minus that half hour time difference. Okay, so I'm using X minus a half. You could have said X minus 30 minutes, but I prefer to keep my time in hours to be consistent with my rates, which are also in hours. So again, Jeff, we don't know how long he's biking for. I'm calling that X. Joan, all I know is that she is biking 1/2 hour less time than Jeff does. So her time is X minus a half. Okay? So we filled out these first 4 values for rates and times. Now we're going to multiply across to get our distances. So 5 times X is 5X. 8 times X minus a half, use parentheses here. So 8 parentheses X minus a half. So we have Jeff's distance and we have Joan's distance. Now in this problem, are these two distances equal or do they add up to some third number like the last problem? Well, think about our picture over here. Are they traveling the same distance? Yes. They both start from Jeff's house, and eventually when Joan catches up to Jeff, they're going to be at the same ending spot as well. So they start at the same place and they end at the same place. So their distance traveled is the same. So to get our equation, we're going to set Jeff's distance equal to Joan's distance. So the equation becomes 5x, because that was Jeff's distance expression, equals 8 parentheses x minus a half, because that was Joan's distance. So there's our equation. Now to solve, distribute 8. 8 times x is 8x, minus 8 times a half is 4. Now I want to solve for x, so I'm going to move my x's to the left side. So I'm going to subtract 8x to the other side. 5 minus 8 is negative 3x, equals minus 4, and then I'm going to divide by negative 3. So we get x equals positive 4/3, because these two negatives cancel out. Now what was that x again? X was time. Okay, this x right here is our time, 4/3. Now what kind of units are on that? 4/3 is hours. Remember how I chose that 1/2 to be half of an hour? So this 4/3 is in terms of hours. Now you probably aren't really used to talking about 4/3 of an hour. So what you might want to do here is convert this to minutes. Let me show you how you do that. If we have 4/3 hours, we're just going to do a little dimensional analysis or changing of units. So if I want to change from hours to minutes, I'm going to put hours on the bottom and minutes on the top, so that when I multiply, these two units of hours cancel out. Well, what's the relationship between hours and minutes? In 1 hour, there are 60 minutes. So to figure out how many minutes 4/3 of an hour is, we're going to multiply 4/3 times 60. You can do that on a calculator. I'm going to do it by hand, and I'm just going to do some simplifying before I multiply. 3 divides into 60 20 times, and what's left over is 4 times 20, or 80. And this is 80 minutes. So 4/3 of an hour is really the same as 80 minutes. Okay? So let's go back to the top and see if we've answered our question. The question was, at what time will Joan catch Jeff? So if you think about how that's worded, you could say, well, we know in 80 minutes Joan is going to catch Jeff. But is that the actual time, the clock time, when Joan catches Jeff? Not really. So what we need to do is convert 80 minutes into the actual clock time. So to do that, remember that Jeff was X. His time was that 4/3 hours, or 80 minutes. What time did he start his journey? What time did he leave his house? Jeff left at 8:30. So 80 minutes from 8:30 is when Joan catches Jeff. So let's get some space down here. 8:30 a.m. plus 80 minutes later is what clock time? Well, 60 minutes later would be 9:30, and I need 20 more minutes to get up to an 80 minutes total. So 9:30 plus 20 more minutes puts me at 9:50 a.m. So at 9:50 a.m., Joan catches Jeff. Okay, that's a tricky problem. All right, let's summarize one last time. We had our distance, rate, and time. We knew the two rates. The time difference with the two clock times gave us two different times in our time column. Jeff's time was X, Joan's time was X minus a half hour. Multiply across to get the distances. We knew the distances had to be equal, so we set them equal and we solved. And when we solved, we ended up getting the time in hours. It was kind of an awkward time, so we changed it back to minutes. And then to get the clock time that corresponded to, we took Jeff's initial starting time, which was 8:30 a.m., and added 80 minutes later to get to 9:50 a.m. And we have our final solution. Alright, that concludes our lecture on solving word problems using linear equations, part 2. Good luck.